So yeah, today I'm going to be talking about container orchestration and our experiences with it at Mesosphere. But first, let me talk a little bit about my background. So when I started my career, I used to be a sysadmin. I used to be responsible for setting up data centers, and over time I transitioned into network engineering. I transitioned into setting up switches, routers, very traditional. But that didn't particularly interest me, so I switched over to software engineering. And what I realized was that we have yet to apply the techniques that software engineers have, the tools that software engineers have to networking and system administration. And my mission is to allow sysadmins and network admins to be able to leverage the acumen that's been developed in distributed systems and to have a proper approach to this versus a lot of hand waving. In addition to that, one of the things that is a challenge that every system suffers is as they evolve their infrastructure, they always have to build orchestration systems to automate it. At Mesosphere, ideally, I want to build a container orchestration system that I can take anywhere and use in the future. So a little bit of an agenda of today's talk. I want to talk about a brief history of how we got here as an industry, and why infrastructure looks the way that it does. How we're trying to make this better at Mesosphere, and some systems that we've built at Mesosphere to enable us to ship this technology. So with this, let's talk about a brief history of networks in the data center. But we can't talk about networking in the data center without organizations. So I want to start in 2007, about 10 years ago. In data centers, and the way that software was run was dramatically different than it is today. In 2007, the term DevOps was not heard of. And we had this clear differentiation of responsibilities. We had QA, we had Ops, and Dev. And these organizations had an adversarial relationship. And the purpose of this was to ensure stability. But it meant that organizations were incredibly slow moving. And software that was developed in 2007 was also dramatically different. Microservices weren't really a thing. People were strapping together SOAs, but you would strap together a SOA by having your favorite enterprise service bus. Also, networking was dramatically different. Networks were these giant layer 2 domains, and this resulted in significant overhead. You typically wasted 50% of your network capacity for redundancy. And all of your components were provided via these big pieces of hardware that were total black boxes. So you had load balancers in hardware, you had firewalls in hardware. And one of the reasons of this was most people ran their own data centers. Whether they bought the hardware themselves or outsourced it to someone like a Rackspace, people weren't able to take advantage of economies of scale. And given that my talk is largely scoped to SaaS companies and internet companies, most of them had statically partitioned systems. You chopped up a system at the beginning when you installed it. It did a few things, and it did them very, very well. But SaaS was continuing to grow at an incredible rate. And among SaaS companies, there became a race to ship faster. And the only way that we were able to keep software alive was by feeding it with sysadmins. And we kept the machines alive by feeding them with blood. And this obviously wasn't working. So in 2008, the industry started to move, and the term DevOps was coined. And a year later, the first DevOps day happened, and the term took off. And DevOps is the application of developer tools to operations. This was also because organizations started to adopt the cloud, and you had to have fewer experts in systems. You had to have fewer experts in hardware. But there was also this notion where we needed to reduce the number of operators. And the only way to do this was using software. Also, software began to change in 2008. Tools like Puppet and Chef to automate operations became popular, even though they had existed for a number of years. We also saw this on the dev side, where we had tools like Jenkins and Capistrano, where we enabled developers to go ahead and deploy software to production without having to consult ops. We also saw the many pieces of software like Hadoop come about and the NoSQLs come about that tended to push hardware much further. But unfortunately, we still had statically partitioned machines, and networking was largely owned by a separate group in the company, and they still had somewhat of an adversarial relationship. But in 2011, a lot of this changes. And this changes because of this technology called SDN, Software-Defined Networking, or an FV, Network Function Virtualization. It's the idea of taking a piece of hardware, or some function that would typically be implemented in a piece of hardware, and implementing it in a piece of software. And the reason of this is that virtualization starts to make massive inroads in the enterprise. And VMs become one of the default ways to deploy things because of this idea of the private cloud. And also the public cloud starts to become reasonable. in 2011, it changed from if you were buying your own hardware, you were an auto startup versus deploying on EC2. Not only this, but software development changed. We started to see these things called microservices come about, and people were still kind of figuring out what they were looking like. But there was an obvious need that we needed better networking to make these work because they had more reliance on the network. And in 2013, this all comes to a head. Dynamic partitioning starts to make inroads in the SaaS industry. Even though several large companies were doing this prior, it finally became accessible to these smaller organizations. And this is largely because these microservices counts explode. If you look at like LinkedIn and Twitter, they talked about how they had hundreds of services running in production. And also, like Google releases their Omega paper. Apache Aurora, the scheduler at Twitter, is open sourced. And we see the Apache Mesos project get a lot of commercial backing. We also see containerization technology finally come to a head. We see Docker becoming released, and it's an instant hit. We also see DevOps from the other side. We see site reliability engineering, which was taking software engineers and having them do ops. So finally, we were able to change things. So everything was changing, but why fundamentally was everything changing? It was changing because of business value. And what that means at the end of the day is money. The benefits of doing all of this were a reduction in cost of goods sold. We were able to have fewer engineers. We were able to have fewer engineers with more servers and more capabilities. And not only did this mean a reduction of cost of goods sold, it meant that we had better availability and we were able to ship features faster to production. Because with fewer engineers, we had less complexity and we had less coordination to do within these organizations. But fundamentally, this all came at a cost. And this cost was complexity. So in the old world, you had something like this, where you had a client that sat on a given node. You had a load balancer at a given fixed IP and port. You had servers, and they'd all be running a given service on the same port. And this was a largely static environment. You never changed its configuration unless you were growing your infrastructure. But in the new world, we were like, well, my app instances might move around. So I need this sidecar that is able to tell me where they are. But my client app has this notion that it has this fixed load balancer, and I don't want to change this. So now we need to add some kind of proxy to go ahead and perform the behavior that my load balancer is used to. And these need to rendezvous somewhere. So I need a centralized registry. And this is a lot of complexity. If we dive deeper into one of these individual containers, we start to see things like IP tables DNAT to become required. And we start to see all these sidecars that add a lot of complexity. And suddenly, engineers have to learn all these terms, VXLAN for overlays. They have to understand what like Raft is for etcd, and this is really complicated. So it was time for something new, and that's where DCOS came about. So the idea of DCOS, it's a data center operating system that is meant to include everything you need to advance from 2007 to today. It includes networking, security, stateful applications, and it orchestrates your data center for you. And the idea is that you're able to do this in your own data center, and if you'd like, you can treat it as a total black box. You don't have to understand what's happening under the hood. But back to our story. Our story starts in November 2015 when Mesosphere first started to build out their network team. And at that time, our network features were pretty limited. All we had was service discovery, and we, again, had this problem with, where are my containers running? And we can't just have them on static ports, and the reason why is because you might have multiple containers that have the same function scheduled on the same host, and therefore these ports have to be chosen dynamically, whereas in the old world, every container had an individual IP. So we have to let Mesos, our scheduler, choose our ports. So fundamentally, how do you find these tasks? You have to have some kind of directory. And the common directory for the internet is DNS. So we built this thing called Mesos DNS. And the way that Mesos DNS worked was that you had your Mesos master that had all of your state information, and Mesos DNS constantly pulled this master. And this was a master that had updates every 30 seconds, every minute. And then all of your tasks were able to go ahead and query this information from Mesos DNS. And this mostly worked, but it had some problems. So it was based on DNS SRV-based service discovery. And for those who don't know, SRV records are these things that contain information about a host name, ports, weights, priorities, etc. And our thought was that everybody has DNS. Fundamentally, it's one of those building blocks and applications in the internet. And even glibc has a bug open to go ahead and support these SRV records, and everyone has glibc. But it turns out this bug was opened in 2005, and nobody really supported this. So we needed a solution that actually worked. Given this, we performed an OODA loop. We wanted to figure out what the rest of the industry was doing. We wanted to come up with some ideas of our own, and then act on them. So we looked at what the rest of the industry was doing about a year ago, and we had these advanced companies that were rolling their own service discovery solutions on top of things like Consul and etcd. We had people who were taking things like Zookeeper and taking client-side stacks like Finagle and pairing them. But we still saw a massive number of organizations with these existing static service discovery solutions, like Amazon ELB or hardware load balancers, and they were really happy. But fundamentally, we realized that service discovery is an afterthought. Nobody wants to do service discovery. Nobody wants to do networking. It's just something that you have to do with these microservices. We also wanted to look at people's assumptions. People assume things like reliable DNS. People assume things like IP per application instance as they're developing their applications. But what we were wrong about is that only some people care about performance, and only some people care about security. The biggest surprise to us was that nobody wants to actually change their application to go ahead and move on to new infrastructure. The idea of changing application code to adapt to infrastructure somehow really scares a lot of the developers that we talk to. And still yet, no one wants to talk to their network engineer. Network engineering has remained this awkward position in organizations, in this awkward department in organizations, where there's still that adversarial relationship. So with that, we came up with some core networking tenets in DCOS. And our core tenets were that DCOS must be agnostic to the environment that it's deployed on. It must be able to run on Azure, GCE, AWS, any cloud in the world. And we should be able to have application developers run their software on our platform without having to adapt to our platform. In order to do this, our platform must provide existing services, so things like hardware load balancers, or things that mimic hardware load balancers at least. And the biggest aspect of this is that we don't want to have to change an organization for them to adopt DCOS, because then it'll never happen. So with that, we decided to go ahead and build some things. And the way that the DCOS architecture worked is that we had a bunch of polyglot microservices. So we had the JVM, C++, Python, Go, etc. It's all deployed on boxes throughout the data center. But what did we end up building? We ended up building a service discovery system, load balancing, and a control plane to go ahead and glue this all together. And with this, we were able to introduce several new Erlang microservices, or services, to the DCOS architecture. And I'm going to go and talk about some of these services. So the first one is our networking control plane, Navstar. And the purpose of the networking control plane is to go ahead and run on every node and to interface with our state store, Lashup, which I'll be talking about a little bit later. And to go ahead and share state information like routing tables, like service discovery records, and push these to the relevant nodes in the relevant systems and subsystems. So things like the kernel, things like Mesos, etc. And I'll be talking about it a lot, but fundamentally what it is it's a building block. It's a building block to go ahead and build the rest of our service discovery on, and it's a building block to build the rest of our networking on. The next system that we built was our DNS story. And we have this daemon called Spartan, and it again runs on every node inside the data center. So previously, in order to make DNS highly available, people did things like this, where they had a hardware load balancer that was running an active passive, or they were using Anycast, and they had some DNS servers behind this. And this infrastructure worked really well for these people, but it had them make the assumption that their infrastructure was 100% reliable, or it allowed them to make that because they had so many levels of redundancy. But without this, the way that normal DNS works is that you have a user with their DNS client and a resolve conf for some sort of reference of the DNS servers. And typically what happens is that your DNS client sends a request to your first DNS server, and you get a reply. And this is great, but the failure case for DNS is pretty awful. So in the not so ideal case, you send a request to your DNS server, and you have to wait at least 1 second for a reply, because with UDP, we don't necessarily get a NAC. We don't get an immediate NAC, and there's not persistent connections here. And the DNS standard advises to think in seconds, because when it was built, that's what made sense. So then we send it to our next DNS server, and we wait at least a second. and then we finally get this timeout. But multi-second timeouts really don't make sense in the modern world. If you're doing things like Ruby or Node.js or Python in your front end, you're single-threaded, and if you're waiting for all of your front ends to wait on DNS as your DNS infrastructure is healing, you can take out an entire application very, very easily. So what Spartan does, Spartan dual dispatches these DNS requests to multiple backend servers. And it allows the first server to respond and goes ahead and forwards a request back to the user. And it sees the second server respond, and it stores that information about availability. And this allows Spartan to control timeouts. So we can do sub-second timeouts. The other thing that it allows us to do is edge DNS. So I mentioned Navstar earlier. And what Navstar allows us to do is it allows us to take third-party components, so things like Active Directory DNS, Mesos DNS, perhaps individuals' independent internal DNS, and it allows us to pump that into Spartan on every node. And this means that DNS it's highly available because every node is independently running their own DNS server. And it also allows us to lower average latency because you never have to go off node to get this data. And we can control DNS in a way that you wouldn't be able to with things like glibc. The next system that we built was Minuteman, or load balancer. And in order to talk about this, we have to talk about how the actual connection process works. So if you have a client, that client calls into the syscall layer, and in the syscall layer, it calls down into the TCP stack, and that does all of its magic. But there's this thing underneath the TCP stack called netfilter, and some of you may have heard of it. It enables tools like IP tables, NF tables, etc. This is all in kernel land, and this is where Minuteman lives. Minuteman goes ahead and interfaces with netfilter and their state store to go ahead and allow you to connect back to servers transparently without having to reason about the fact that you're connecting through a load balancer. But let's dive in to a little bit more detail about how this works. So again, we have our state store, lashup, that tells us that there's a VIP that exists, a virtual IP that exists with a given IP port and a set of backends. And Minuteman goes ahead and whispers this data to the kernel to program in these exceptional flows. And when the user first connects to this given application, the kernel punts that connection over to Minuteman, and we can go ahead and write a mapping to the backend that we want for that connection. And then this connection goes through the kernel for the rest of its lifetime. So the benefits of Minuteman are that it gives the appearance of a fixed load balancer, and it's fully distributed again because it runs on every independent node. And we were able to take advantage of the kernel's data plane. And the fact that it's written in Erlang it's really nice because the latency guarantees that we're able to provide for time to first byte can be tightly bounded, since every one of these connections is an individual process. But these systems aren't particularly interesting by themselves. We have to talk about how we tie this all together, and I think that this is the real innovation in our system. So there's a bunch of global state in this system that I talked about. So these load balancer task mappings that we have in Minuteman. We have these DNS zones with independent records. We have these routing tables, and we have implicit information like reachability. Is a node up? Is a node faltering? Etc. And this is a fundamental problem when you have a lot of computers because you have constant churn amongst all these computers. Virtual IPs might be going up and down, tasks might be starting and stopping, and you're trying to figure out the availability for your neighbors. And sometimes these computers break, and sometimes a lot of these break. But sometimes you don't know if they're broken or not. They're in this kind of weird state. And fundamentally, it's a signaling problem. It's a problem of how do you go ahead and message to all of the nodes that require this information what the state of the network is and what the state of all the nodes are. And the typical answer to this is use Zookeeper. Because it's something that's been around for 10 years. It works. Hadoop uses it. It's a reliable system. But at Mesosphere, we know about Zookeeper. Going back to our microservices architecture here, Zookeeper is kind of at the center of our architecture. We know how it fails. And we know how it works. And it works pretty well, usually. But when you have things like network partitions occur, it fails in dramatic ways. And you really don't want this when you're on an on-prem environment and you have no sysadmin or you have no software engineer to go ahead and fix this. So we said, well, how else can we do this? And the naive answer is what we have in distro today, which is everyone just kind of connects to everyone. And the OTP team is working on this, but we needed a solution about a year ago. And the problem with this is that it generates a massive amount of information. And every computer would just be sending out TCP packets all day long, and you wouldn't actually be able to get anything done unless every computer was its own little supercomputer. So we thought, well, who else has solved this? And with that, we looked at academia. And it turns out that academia has spent 10 plus years on figuring out how to do things like failure detection, on how to do things like building efficient overlays. And with this, we came up with our control plane, Lasha. And we said, well, how do we scale this naive approach? How do we scale this naive approach away from a complete graph? And we realized that we don't need a complete graph. In fact, we just need a sparse connected graph. But how do you go from having these discrete nodes that are all over the place to having this connected graph? And how do you do this in an efficient manner? So we looked at this protocol called HyperView. And HyperView is this protocol that allows you to have a fixed active view to a given set of nodes. So, and this is a constant number. In the examples here, I'm going to be using a 3. In production, we use 7 because in the paper they talk about some of these tunables, and we've tuned our system to about 10,000 nodes. So at boot time, you have a little bit of information. You have these contact nodes, these leaders inside of the network. And when I mean leaders, I don't mean leaders in the sense that they're actually orchestrating very much. They're just nodes that are always going to be available at a given address. And they only need to be up at boot time. So when a given agent comes up, it can go ahead and connect to these nodes. And since they haven't violated the size of their active views, they are perfectly fine accepting these connections, and we can build up the network. But if more connections or more nodes connect to them, they have to shed some of their previous connections, and they have to shrink their active view in order to maintain that K. And they can go ahead and ask nodes to connect to other nodes in the network by forwarding these join requests and shedding this load from the core of the network. And with this, we're able to build up this graph, and these messages are forwarded throughout the network until we finally get a connected graph. It's a connected graph, but it's an incomplete graph, which allows us to have low replication, but it allows us to have redundant paths in the network. But this isn't particularly interesting. This isn't particularly interesting unless it responds to failure, because we have this problem of reachability information. We have this problem of, do we know a node is up or not? And if every node still had to pessimistically health check every other node, we would have massive overhead still. So with this, we came up with the idea of constant adaptive health checks. And a lot of this was borrowed from the swim work and in a gossip-style failure detector. So let's say that you have 4 nodes, A, B, C, and D in this case, and A fails. Now, if every node is health checking every other node every 200 milliseconds, let's say, or every one of its adjacencies every 200 milliseconds, you're still going to generate quite a bit of information, and you're still going to require these tight timer loops. And there's a lot of negative side effects because we're running along other processes, and those other processes might be massive JVMs, they might be Hadoop, they might take up the entire machine. So we can't have constant health checks that are very, very tight in interval. So instead we said, well, why not ensure that every machine is health checked every so often, but given that it has enough adjacencies, we can rely on the majority vote to decide whether a node is down or not. So when a node fails, or when we think a node fails, let's say that B has observed A has failed, it goes ahead and messages to C and D and it asks, have you seen it fail as well? And if those nodes have decided that that node has failed, they go ahead and they disconnect from it and they route around it. And the HyperView protocol runs again, and you go ahead and you build up your graph. But how do we do routing on this? In the example earlier, I talked about 2 nodes sending messages to each other that weren't connected to one another. And we aren't making connections on demand because, again, that would require a ton of overhead. And TCP really doesn't do well with lots of making and breaking. So fundamentally, if you have a graph, if you, the entire network, you're able to go ahead and do routing across it. But unfortunately, not every node has this entire view. We have to build it up. The only thing a node knows about is its local nodes, the nodes that it's immediately connected to. But you can go ahead and build up this adjacency list. You can go ahead and say, for every given origin, what are the destination nodes that it's attached to? And what we do is we go ahead and we gossip these view changes. So when there's a make or break or a health check failure, we go ahead and we randomly gossip this throughout the network. And we version these adjacency lists to go ahead and know whether we've gotten an old message or whether this is an actual new active view. And with this, every node can build up an internal state that models the entire network eventually. And once we have this, all we need to do is run Dijkstra across it, and we're able to build up a minimum spanning tree over the network. So once you have this graph, and once you have routing and failure detection, it actually turns out that it's pretty easy to go ahead and build a database on top of it. And this is where we are able to store things like task mappings. And we use these things called CRDTs. And CRDTs have actually been really, really popular in the Erlang community. But for those who don't know, they're these data structures that allow you to make simultaneous changes across multiple systems. And once all messages QS from the network, you can merge the state and get a valid state that converges at the end. So in our case, we use the CRDT KV store to go ahead and launch tasks on multiple nodes, write it to our local KV store, and then gossip or message these throughout the spanning tree. And then when this data converges, everyone has a global view of all of the tasks that are running inside of the data center. So I wanted to show you guys a demo, but unfortunately the Wi-Fi was flaky, so I scripted some of this. But in this demo, we have 3 nodes running Erlang, foobar, and baz. And these nodes are in a full mesh. In Lashup KV, we have this nice little API that says, for this given key, Erlang users, what's the value? And I wanted to go ahead and break apart these nodes and make it so that we don't have this mesh anymore and make the topology look something like this. So bar and baz are not directly connected. Now on bar, if we go ahead and we request an op to that key and we say, let's take a value and increment it by 5. That value actually goes ahead and converges on all the nodes to 5. But let's go ahead and make this even a worse scenario. Let's go ahead and partition all the nodes away from each other by changing the cookie. So now all of these nodes are independent islands. And if we go ahead and we ask them to increment by different numbers, we see divergence in this data because they aren't able to go ahead and message each other. And if we go ahead and we rebridge this, we see convergence across all of these values. So Lashup KV is it's a database that has quite a few data types, and we were able to leverage existing CRDT libraries to go ahead and do this. But fundamentally, this is an interesting system. But does it actually provide business value? Is it any better than Zookeeper? Is it any better than what's out there already? So prior to Lashup, we did this test where we used Minuteman, our load balancer, and we sent several hundred requests per second through it. And we wanted to look at what happened in failure. So we failed 10% of the nodes in the network. And we wanted to see what happens to throughput and what happens to latency. And we found that throughput was heavily degraded for about 90 seconds. And average latency went up to 1 second, which was the retry interval for TCP. But once we instituted Lashup, we saw the same test, and throughput had no effect. And there was no effect on latency when we did this because we were able to detect failure before the next TCP connection occurred. So Project Lashup, it's a novel distributed systems SDK that's enabled us to ship these systems in our network and in our product. And it provides several services today. It provides global membership. It provides multicast delivery using that spanning tree. And it provides a strongly eventually consistent data storage. And it's actually powering real systems that we're shipping on-prem today. And it's an open source project, so anyone can use it if they want to. It's made as a library, so you can embed it inside of your own system. But I want to talk about Erlang now. I constantly get this question, well, why Erlang OTP? Why not Go? And Go has made incredible inroads in the container community, in the orchestration community. And in fact, we tried to use Golang. The first version of Minuteman, or load balancer, was actually written in Go. So we thought, well, why not stand on the shoulders of giants? Why not leverage what's already out there rather than having to reinvent the wheel? Because much of what we're doing is it's already been done. Fundamentally, we're building systems over and over again. We were building things like RPC over and over again. We were building failure detection over again. We didn't want to do this. So we said, well, what's a good language with a healthy set of distributed systems and networking libraries? And we said, well, what's one that has an ecosystem? And what's one that has an ecosystem that's been battle tested for a number of years? Because when it's 3 a.m. and your system fails, and when your system fails on someone else's data center, who do you want to pick up the phone? And the answer is you don't want anyone picking up the phone. You want your software to automatically deal with failures, and you want your software to automatically deal with the exceptional cases. Because oftentimes, upgrading our software inside of our users' data centers is harder than upgrading software on the Mars rover. There's a story that the first version of the software on Curiosity had some bug in it, and in 24 hours they were able to upgrade it. But when we're dealing with these incredibly conservative organizations that are deploying the software on premise, we have to rely on our software self-healing in the period between a bug being detected and us actually being able to resolve it and ship a new version. So with this, what components of Erlang were we actually able to use that were battle tested and provided these benefits? So one of the first things that we needed was a durable store. We needed to be able to go ahead and write data to disk. And again, in Go, we had to go ahead and use some third-party library. But the fact that we have Amnesia already built in, although sometimes it does get a bad rap, it's an incredibly useful library that we can rely on. And it's been battle tested. It's like 20 years old, and it's older than Go itself. It's older than most of the other languages in our stack. And the next thing that we needed was a CRDT library. And CRDTs are these incredibly finicky data structures. They're really hard to implement. And people have spent their entire careers trying to make them and invent new ones. And we actually couldn't find another CRDT implementation that was used in production that was open source in any other language than Erlang. And this was due to Basho's implementation in React KV. And they've done extensive testing on it. They've done extensive property testing on it. And the fact that other users have actually deployed this on production and rely on it for their critical infrastructure was really valuable to us as a signal. And the next thing that we needed was a secure distribution channel, because some of our users actually cared about security on the network, because they were running on these untrusted clouds. So again, we were able to go ahead and do things like leverage distributed Erlang's own SSL, and we knew that people were using this. And we knew that we could rely on it and switch it on as a configuration flag as opposed to having to roll our own encryption. If you look at other service discovery solutions and other networking encryption solutions that have been implemented in, say, Surf, they had to roll their own encryption. And we all know that's incredibly dangerous. So moving away from FlashUp, moving to Spartan. Spartan needed a DNS server. So we were looking at third-party DNS servers, and we were looking at saying, well, what if we go ahead and we adapt something to DNS mask or bind? And this turns out to be really hard because they're not written in a modular way. But the Erlang community, again, provided us a great DNS server. We found that DNS Simple, a company whose business is serving DNS, had open sourced their DNS server. And they were using this in production at relatively large scale, more scale than any individual node would ever need. And Minuteman also needed a kernel API library using this thing called Netlink. And Netlink is a protocol that you talk to the Linux kernel with in order to do things like programming routes, programming net filter rules, etc. And we found that, again, another company, TravelPing, had open sourced a library. They'd open sourced a library under a liberal license, and they'd open sourced this library that had been battle tested on other sites. And being able to leverage this without having to do things like roll our own protocol or worry about the GPL or worry about a community that was putting out libraries that weren't necessarily used in production was really valuable. And then the last thing that we leveraged from the community was a graph library. And we leveraged what's built into Erlang called digraph. And it's a simple graphing API or a graph manipulation API. It has things like Dijkstra built into it. It has quite a few nice algorithms built into it. But it didn't work for us. And it didn't work for us not because it wasn't able to provide the right features, but it wasn't able to work with us because it was too slow for our use cases. And it was a little bit heavy for our use cases. We need these sender-based trees. So we went ahead and we built our own library. And this is where testing became really valuable and in what Erlang gives you in testing. So we were able to verify our own routing implementation against digraph. And the way that we did this is using property-based checking with proper. So we were able to automatically generate the command sets of what could happen inside of this network. And we were able to verify equality across both our implementation and the implementation that we built on top of digraph. We were able to do this tens of thousands of times. It's something that you couldn't reasonably do with unit testing, something that you couldn't reasonably come up with as a human. And the other thing that we did for testing was common test. So common test makes integration testing wildly easy. And on every check-in, we run quite a few common tests on LashUp. We spin up many virtual nodes. In our default case, on every check-in, we spin up 25 because that's what our CI infrastructure supports. And we're able to torture test our infrastructure. We're able to partition our infrastructure. We're able to cause disk errors. We're able to crash nodes and see how the system responds. And we're able to verify that the invariants that we stated still hold. And the benefits of this aren't that we have this infrastructure. The benefits are that this is built into Erlang and this is built into our community and culture. Because with 500 lines of tests, with 500 lines of integration tests, we're able to get 80% code coverage. And we're able to add more code. And largely, this code coverage metric still holds. So the takeaways I want to give here are that the container ecosystem is still in its early stages. I think we're still figuring out what we need to build. But that Erlang is suitable for building modern, reliable distributed systems. I think that a lot of organizations haven't looked at this because we constantly talk about how the Erlang ecosystem isn't really ready for everyone to use yet. And we have this discussion of, packaging is hard, but it turns out that there's all these solutions that are out there that are battle tested and that are used by real companies. And with that, thank you. Questions? Flapping? So yeah, there's several cases that flapping can occur in, but we have dampening in the protocol. So there's flapping where a node is actually fundamentally failing, and that resolves itself by having backoff. And then the other thing is that we have a defensible protocol. So if a node is overwhelming us, we can tell it to go away. So we don't have any interest right now in that, mostly because none of our systems require that. But LashUp is an SDK, so plugging in your own CRDT implementation wouldn't be particularly hard, especially if you implemented it as a React DT behavior. Oh, due to end? I'll go ahead and share this after the talk. Anyone else? Great, thank you.